Hello, my name is Jared DeLuca, and today I'll be reflecting on my capstone project titled BrainGround, a closed-loop neurofeedback BCI with EEG and VR integration. This project explored how brain-computer interface technologies, specifically EEG-based neurofeedback, can be combined with virtual reality to assist in self-regulation of emotional states such as anxiety and depression. The system uses EEG signals from the F3 and F4 regions of the frontal cortex to measure emotional markers and dynamically alters a calming VR environment in real time to provide users with visual feedback about their mental state. The overall goal was to demonstrate that accessible technologies could create an engaging, user-guided platform for anxiety self-regulation. This platform aims to provide a portable, personal brain training application suitable for emotional regulation. The methodology I followed was a systematic engineering design approach. Early research indicated that frontal alpha asymmetry, particularly in the upper alpha band, is strongly associated with emotional processing. To build the system, I first designed a modular pipeline for data acquisition, signal processing, GUI development, and VR integration. Several approaches were trialed, including OpenVibe and C++ libraries, but ultimately I chose Python-based tools like MNE, SciPy, and PyQt for their flexibility, real-time capabilities, and strong community support. Panda 3D and Blender were used to create a lightweight VR environment where lighting conditions could dynamically change based on the user's neurofeedback score. This methodology was appropriate because it allowed for rapid prototyping, real-time processing, and integration with open-source VR engines, aligning well with the aims of accessibility and modularity. The main outcomes of this project were a fully functioning prototype capable of reading EEG signals, calculating frontal alpha asymmetry scores, and delivering real-time responsive feedback in a VR world. Although the system operated on a pre-recorded EEG data during development, it was designed to easily extend to live EEG hardware. Findings confirmed that the Python ecosystem is highly suitable for rapid prototyping. Key recommendations for this project for future work include incorporating labeled emotional data sets to validate classification accuracy and expanding feedback mechanisms beyond just lighting, for example, adding sound, environment, or avatar interactions. Additionally, testing other EEG frequency bands like theta, delta, and beta could open new dimensions of emotional detection beyond upper alpha asymmetry. One aspect of the project that I feel was exceptional was the real-time performance achieving using multiprocessing. Even with modest hardware, the system maintained seamless real-time feedback with minimal latency from EEG signal acquisition to VR lighting changes. Another outstanding feature was the modular software design, which ensures the system is highly extensible for future developments, such as switching VR engines or adding alternative neurofeedback strategies. Reflecting on this project, I learned two key things that will benefit me in future deployment. First, I learned the value of flexibility and adaptability when choosing technical solutions. Although OpenVibe and C++ appeared attractive initially, critically reassessing and pivoting to Python allowed the project to succeed within the time and resource constraints. Second, I gained a deeper appreciation for interpreting scientific measurements responsibly. In neurofeedback, how you define and interpret metrics like frontal alpha asymmetry is crucial. Careful mapping and documentation are essential to maintain scientific integrity when building user-facing systems. Overall, BrainGround has demonstrated the potential for low-cost, accessible EEG VR systems to assist in emotional self-regulation and lays a strong foundation for future work in this exciting field. Thank you for listening.